Routh Case 3 is where you have an entire row of zeros when you're building the Routh array. Let's start with our characteristic equation. Delta of s is equal to s cubed plus s squared plus 2s plus 2. So let's go ahead and construct the Routh array here. So s cubed begins with 1 and 2. S squared is also 1 and 2. So next we're going to build the S1 row by calculating B1. So you'll notice as you do more of these examples that when you have a pattern where two rows seem to be repeated, that you're probably going to end up with a 0. So here we can see that as we calculate B1, the value is based on the product of 1, 2 minus 1, 2 divided by 1. So here, 2 minus 2 divided by 1 is equal to 0. So the next value, because we're going to be multiplying by this column here that doesn't actually exist, is also going to be equal to 0. So B2 by inspection is just equal to 0. So we have two zeros here. So in order to solve this now, we can divide through, if we like, we're going to create a value of epsilon for the left-hand value here because that was calculated to be 0. So we choose this value of epsilon. And now when we calculate S0, again we're going to calculate epsilon times 2 minus 1 times 0 divided by epsilon. So this value is going to give us 2. So you might ask, how come we didn't make this value epsilon? Well, the reason is that this 0 comes from the fact that there are no values here. So it's not that epsilon is for any value that happens to be 0. We use the value epsilon here because the product result that we got from calculating this submatrix was 0. So it was a product of real numbers that gave us 0. In contrast, the 0 that we got here was based on the fact that these values don't exist. So we leave it as a 0 here and we make this value to be epsilon. So with this value of epsilon, 2 epsilon minus 1 times 0 divided by epsilon is equal to 2. So we go ahead and take this value. So now we look at the first column. All of the values are positive, but we have this epsilon that we don't know what to do with. So we take the limit as epsilon approaches 0 from the positive side. And in doing so, we see that this limit as epsilon approaches 0 is 0, but positive 0. So we can conclude from this that the system has marginal stability. So the reason that the system is marginally stable is that there are some inputs for which the system is stable. And we also have two roots on the j omega axis. So again, if you ever have a full row where the values are both 0, then the row above is the row that tells you how many poles you have on the j omega axis. So because this is s squared, it tells us we have 2 poles on the j omega axis. So we have 2 roots on j omega. Let's go on and look at the next example. So here's another example of case 3. Delta of s is equal to s to the 5th plus s to the 4th plus 5s cubed plus 5s squared plus 6s plus 6. So you may want to pause the video here so that you can do this example first and then you can check your work. So go ahead and push pause and then perform the Routh array and then you can check your result with the result that I get. So the first element that we're going to create, the first row that we're going to be creating, is based on S5. So we're going to pick the coefficient for s to the 5th plus s cubed, 5s cubed plus 6. So our first row is going to be 1, 5, and 6. The second row that we're going to pick, s to the 4th, is again based on inspection. 1, 5, and 6. So just like in the previous example, we see that we have a pattern here between the two rows. So we're going to build B1, again, the product of this determinant divided by minus 1. So 5 minus 5 divided by 1 is equal to 0. When we calculate B2, 1 times 6 minus 1 times 6 divided by 1. So these are real values that we're calculating that come out to be 0. We don't have any zeros that are here because we're missing elements of the Routh array. These values are 0 based on existing coefficients. So we now get two zeros, one after the other. So again, this tells us that the row in s to the fourth indicates the coefficients of a transfer function, auxiliary function, delta 1 of s, which is one of the roots of the system. And that tells us that we have 4 poles here in this example that are on the j omega axis. So we can go ahead and write that auxiliary equation as s to the fourth with coefficient 1 plus 5s squared plus 6. So we can verify, if we like, hold on, so we can verify, if we like, that the auxiliary equation is actually a root of the system by using synthetic division. So we divide s to the fourth plus 5s squared plus 6. Let me rewrite the 6 in here, into our original characteristic equation delta of s. So in doing this, first we multiply by s, and then we get s to the fifth plus 5s cubed plus 6s. We can subtract those elements away to get s to the fourth plus 5s squared plus 6. So now if we add plus 1 to our result, we find that we have no remainder. So s plus 1 is another root, and s to the fourth plus 5s squared plus 6 is the pair of 4 roots that are on the j omega axis. So we can go ahead and add 2 values for epsilon here and continue with the Routh array. So we did the synthetic division over here to verify to ourselves that we hadn't done something wrong, right? So this demonstrates that s plus 1 is definitely one of the roots. But we can go ahead and continue with the Routh array with these values of epsilon to check to make sure that we don't have another value that turns out to be in the right-hand plane. So if we hadn't done that synthetic division, we could continue on. So we calculate C1, which is the first element of the s squared row, to be 4, because we multiply 5 times epsilon minus 1 times epsilon divided by epsilon. For C2, 6 times epsilon minus 0 divided by epsilon is 6. For the S1 row, now things are going to get interesting. 4 epsilon minus 6 epsilon divided by 4 gives us minus 2 epsilon over 4, or minus epsilon over 2. And for S0, the value is equal to 6. So this is interesting. Here we have an epsilon value, and here we have essentially a minus epsilon value. What does that mean? Well, it turns out that these two elements in the matrix tell us that we have pieces on the j omega axis. The fact that we have 2 rows that would have been 0 as epsilon approaches 0 tells us that we have 4 poles. Because we have s to the fourth, we know that there are 4 poles. But s to the first is also going to be 0 as epsilon approaches 0. So that tells us again that the s squared term is going to be one of the roots, or in this case 4s squared plus 6. So now 4 poles on the j omega axis is the result that we get from the Routh array. A full row of zeros again tells you that you have roots on j omega. If you actually look at these roots in MATLAB, you'll see that they come out to be 0 plus or minus j 1.73, minus 1, and 0 plus or minus j 1.414. So the interesting thing is that MATLAB actually gives us, I should have a minus here, oops. MATLAB actually gives us -0 for one of those values. So that corresponds to the fact that we see that we have a negative e over 2 here, right? So as we let epsilon approach 0, we get -0 as the entry in this left-hand column. So it's a 0 value, which tells us that the pole is on j omega.